Hey guys, my name is Eric and this is example 5 from slide 95. It's going to be a network of two CSTRs. So you can see we have a flow in and then we have a flow out of each tank. So in here, out to here, and then finally out. The unique thing about CSTR problems is you have two things going on. One of which is that the concentration inside the entire tank is going to be uniform because it's being stirred. And then the other thing is that the concentration inside the tank is going to be equal to the concentration of the flow out of the tank. So where we're going to want to start off with this problem is getting to our mass balance. Now you can see here, for our mass balance, accumulation equals in minus out plus generation minus consumption. In this case, we don't have any generation or consumption because of it's just a mixture. It's no reaction. So first off, what we're given, we can fill in our variables. So we're going to have the concentration initial. And then here, concentration CA1 is going to be the same, like I said, as the flow rate, or as the concentration flowing out. And then CA2 is going to be our concentration in the second tank, which will be equivalent to the concentration of the flow out. So as the problem states, we're going to have all of the same flow rates. So that's going to be 4.5 meters cubed per hour. So we can see that the flow rate is the same in and out of each one, so there's not going to be any accumulation of volume. It's going to remain the same. Okay. And then our volumes inside are going to be 1.9 meters cubed here, and then 1.15 meters cubed here. And that's going to be all of our given information. Now, the other thing about this problem is we're going to assume constant density. So that's going to help us out because our mass balance here would normally be concentration times volume times density. But we're going to have density as we're just going to be able to cancel out density. So our mass is just going to be concentration times volume, which makes it easier on us. We're just not going to assume that the density is going to vary in here or in here if it accumulates more or less of the sodium hydroxide. So we're going to move down and let's start with our mass balances. So you're going to want to write two mass balances since we have two tanks. So we're going to be mass balance, tank 1. And then let's do our mass balance for tank 2 over here. Starting off, our mass balance for tank 1, or the first reactor, is going to be, we're going to write it as a differential. So it's going to be dCA1 V1. So concentration times volume over dt. And it's going to be the volumetric flow rate in times the concentration in. And then it's going to be minus the flow rate out times the concentration out, which is going to be CA1. And then we need to identify some initial conditions, which is going to help us out further down the line. So we're going to make sure we know that at t equals 0, as the problem states, CA1 is going to be 0 since it's just pure, what is it? Yeah, pure water enters, so that's going to be 0. And then, oh, I'm sorry, no. Pure water's flowing in. CA1 is a concentration in the tank 1, so that's going to be 20 volume percent. And that's our first mass balance. Second mass balance, we're going to look at what's going into here and what's coming out. So we are going to write this as d CA2 V2 by dt equals volumetric flow rate CA1 minus volumetric flow rate CA2. So you can see we have in both sides we have accumulation equals in minus out. All right, and then our initial condition for second reactor is going to be at T equals 0, CA2 of 0, sorry, equals 40 volume percent. Okay, moving on, we're going to leave mass balance for tank 2 for later, and let's solve our mass balance for the first reactor. So what we can do here is we can see that volume in all of these tanks is going to be constant because it's a same flow rate in as flow rate out. So what we can do is go ahead and pull out V from our differential. So we're going to write this as V1 dCA1 dt equals VCA not minus V1 CA1. Now we know that, so since this is the balance of the sodium hydroxide coming in, we know that it's pure water coming in, so we can actually just get rid of this term. This is going to be 0 because there is no mass of sodium hydroxide coming in. So then next step we're going to want to do is we want to isolate our differential over here on the left. So we're going to divide both sides by V1. And so that's going to leave us with dCA1 by dt equals negative V1 V dot 1 CA1 over V1. Now this is going to be an interesting concept. It's called space-time. So actually this term here, we're actually going to turn that into tau 1. So what we're going to do is, so this is a volumetric flow rate over volume is volume over time over volume. Volumes are going to cancel. That's going to be 1 over time. And we're going to use tau to represent that. So we will switch it to, and then this is going to be 1 over tau. Oh, sorry. So then we're going to rewrite this as a dCA1 dt equals negative CA1 over tau. Tau 1. We're going to label this tau 1. So next step we're going to have to get to is separation of variables. So we're going to move it to this form. We're going to do 1 over CA1 equals, dCA1 equals negative 1 over tau dt. This way we have our dCA on one side and our dt on the other, and we're going to go ahead and integrate both sides. Ends up with ln CA1 equals negative t over tau 1 plus k. We have a constant here because it's indefinite integration. And then we're going to have to exponentiate both sides to isolate CA1 equals e to the negative t over tau 1 plus e to the k. And then what we're going to do here, since k is a constant, we can just rewrite e to the k as a constant. And then, well, actually this k is going to move up top here because of the rules of exponents. We can put it in there. And then it's actually still a constant, so we can just then move it out front here as k. So we'll write CA1 equals k e to the negative t over tau 1. And then we can plug in our CA1 0 to the k, since that one is going to be also a constant. So this will be our final mass balance, what we solved for. So CA1 of 0 e to the negative t over tau 1. And that's why it's useful to do our initial conditions here, because we'll be able to plug that in here, which is going to be the 20 volume percent over here. But we don't need to worry about that right now. So then next up, we're going to take this mass balance for reactor 2, and we're going to start on our second mass balance. Now this is where it's going to get this is where it's going to get kind of crazy. So I'm going to do my best to break it down step by step, and we will get there together. So what we're going to do for mass balance 2 is we're going to also pull out V2 because, like we said earlier, the volume is going to be constant. So V2 d CA2 dt equals VCA1 minus VCA2. And these are V dots because they're volumetric flow rates. And then we're going to do the same thing as we did last time. We're going to use the space-time. So it's going to be 1 over tau. Actually, I think I misexplained it earlier. So on a side note over here, V dot over V is going to be 1 over tau. 2. So going in here, I'm gonna do 2 steps in one. I'm gonna factor out this V, and then I'm also gonna divide by this V2. So we're gonna end up with dCA2 dt equals V dot over V2 times CA1 minus CA2. And then that's just going to equal 1 over tau 2, CA1 minus CA2. Okay, moving on. We're going to go ahead and we see that we have a CA1 here. And then that's what we solved for in the first mass balance. So we're going to pull this down here and plug it in. And we're also going to distribute the 1 over tau. So what's this going to be is it's going to end up as one over tau 2. And then plugging in CA1, that's going to be CA1 naught e to the negative t over tau 1. Keep in mind these are 2 separate variables, or I guess these are constants actually. T1 and T2, tau 1 and tau 2. So just keep that in mind. Be careful on your notation. so you don't mess yourself up further down the line. And then minus 1 over tau 2 times Ca2. So this is the point in which I got really confused in class when Dr. Lee went over this problem. This is going to be our, we're going to use the integration factor method. So I'll do a little side explanation of this. So we want to rearrange it till we get into the form of dy dx plus p of x y equals q of x. Except we're not using y and x, but this is just the basic form of it. And then our integration factor is going to be e raised to the power, or raised to the integral of p of x dx. And then that's going to help us simplify our equation. So now we want to rearrange. So what we're going to do is take our equation, and we're going to pull the 1 over tau 2 Ca2 to the left side. So it's going to be dCa2 dt plus 1 over tau 2 Ca2 equals 1 over tau 2 Ca1 naught e to the negative t over tau 1. And then, as you can see, there's a dy, and then that's our y. So this is our y here. And then this is going to be our p of x. And this entire thing here is going to be our q of x. Put a little note right here, dy dx. Oh. Just so we can keep seeing that. Okay, perfect. So now we're going to move on. And then this is where our integration factor comes into play. We're going to want to multiply both sides by the integration factor. So we're going to find our integration factor real quick. In this situation, it's going to be I of t. And it's going to be e to the power of the integral. And p of x is going to be this 1 over tau 2, so 1 over tau 2 dt. And then so easy integration there, it's just going to be e to the t over tau 2. So we're going to take both sides of the equation and multiply them by this integration factor, but for simplicity, we're just going to keep it written as I of t. dCa2 dt oops. Okay. So this is where it helps us simplify. It's a little bit hard to see with all these crazy variables we're working with. So I'll do what I did earlier and write it. So basically it's gonna be kind of a product rule situation. So we can rewrite the entire left side. So imagine it as being d by dx of ix y, which using it's like we're pretty much doing the product rule in reverse. So the product rule says that it's going to be, I remember it being like f prime g plus f g prime, right, from Calc 1. So there's your f prime g, your g is going to be the y, so dy dx plus I of x y. So that's what we have over here. This is pretty much what we have all the way on this left side. Like I said, it's a little hard to see, but if you think about it hard enough, it makes sense. So we're going to rewrite this entire left side as just dix t CA2 dt. And then we're going to keep the right side the same. I'm going to simplify it, or just write it in a little bit of a better form. So CA1 0 e to the negative t over tau 1 all over tau 2 times IT. From this point, we're going to take both sides and we're going to multiply them by dt. So then we end up with dit CA2 equals CA1 not e negative t over tau 1 over tau 2 IT dt. Next step, we're going to want to integrate both sides. Now, this time we're not going to do an indefinite. We're actually going to use bounds on our integral. So we're going to go from 0 to t dit CA2 equals integral from 0 to t CA1 e to the negative t over tau 1 tau 2 IT dt. And then we'll go ahead and just start with integrating the left side. So I guess I'll just box this off and we'll come back to that. So we'll just do this side is going to be, it's going to come out, this is a simple integration. This d is going to disappear, and then we're just going to end up with I of t CA2 times our upper bound, or it's CA2 of t because we don't have that dt over on this side, so we're just going to make CA2 a function of t. That's my understanding of it. That's the best way I can explain it. Minus I of 0 CA2 of 0. That's our left side solved right there. The next thing I can say is if you look over here, take our I of 0 and then our I of t. So we're going to take 0 and plug it into t. And since that's going to go in the numerator, that's going to be e to the 0. As we all know, anything to the power of 0 is 1. So then we can just get rid of that term, and it's just going to be I of, since that term is 1, minus CA2 of 0. Now, next up is going to be solving our left side, our right side. So we're going to bring that down here, and it's going to be, let me give us a little more room. Integral of 0, well, we have it right there. So looking at this, what I'm going to do is I'm going to pull out all of the constants to the left side of the integral to make it easier to see what we have going on. And then at the same time, we're going to plug in I of t. We're actually going to write what that is because that's inside of our integral and it's a function of t, so we can't pull it out. So over on the left side, we're going to end up with CA1 of 0 over tau 2. And then the rest of those terms are in terms of t, so we're going to write those in here. This is, so a little side note, just to save a little bit of space. These both are going to come over here. It's going to be e to the negative t over tau 1. And then times our I of t is e to the t over tau 2. And then they will just combine together. We can add the exponent. So writing that down here is going to come to our integral from 0 to t of e to the negative t over tau 1 plus t over tau 2 dt. Now, from this point, we're going to do a u substitution. In class, Dr. Lee did a u substitution, kind of skipped a few steps. It's the fast way you can do it if you're really good at u subs in your head. But I know that confused me, so I like to write out my u sub. Let's pull this over to the side. So we'll have our u sub here. Now we're going to want to make our u equal negative t to the, or over tau 1 plus t over tau 2. That's going to be e. We want it to end up e to the u. That's the way we want to do our integration. So derivative du is just going to be negative 1 over tau 1 plus 1 over tau 2 dt. Isolating our dt on the right side, we're going to pull this over to the left. We're going to write it at, we're just dividing both sides by this entire term, basically. So it's going to be 1 over negative tau 1 plus 1 over tau 2 du equals dt. Okay, and I'm going to just block this off again and work with our right side for now. Give us a little more room here. So keep those constants out front. And then we're going to want to redo our bounds to fit our u sub in terms of u, basically. So we'll take the t, plug it into u. We're plugging it in for t, so it's going to be the same. So negative t over tau 1 plus t over tau 2. And then for our 0, plugging in 0 to t here turns into 0. And then it's going to be e to the u du. I like that. Looks a lot better because integrating e to the power of a function is super easy because you just plug it in. So it's going to be, oops, that's not equals. It's just going to be e to the negative t over tau 1 plus t over tau 2 minus e to the 0. And then let's bring our left side back in play. And we are almost at the finish line. So rewriting. I'm also going to plug in the I of t over here on the left side. I'm going to plug back in our I of t from up top. So e to the t over tau 2 times CA2 of t, it's a function of t now, minus CA2 of 0 equals our left side, our right side. But we have an e to the power of 0, which is just going to equal 1. Now this here is basically our final answer, or it's how we're going to solve for t. All we have left to do is just rearrange. So if we look back at what the question asks, is we want to find the time required for the stream leaving the second tank to reach a concentration of 5 volume percent. So what we're going to do is we're going to solve for CA2 of t, which is perfect. because it's a function of t. So all we're really going to want to do is just rearrange for CA2 of t. So CA2 of t equals CA1 of 0 times 1 over negative tau 2 over tau 1 plus 1 times e to the negative t over tau 1 minus e to the negative t over tau 2. You see I just broke those apart and then flipped them around. Plus CA2 of 0 e to the negative t over tau 2. And you can see that what we ended up doing was taking this here and we took it around and we divided it. So that's why we ended up flipping the sign over here and over here. And then last but not least, I'm just going to show you what I did for this part. Instead of writing it all out, we're just going to plug in all of the given info. So here, we're just going to take all of everything. So right here is going to be the mass fraction, or actually it's volume fraction is what it gave us, volume percentage, times the density to give us mass. So I did that for each and every one of them. All of these numbers get plugged in or plugged into here. And then that gives you this big long thing. Solving for t algebraically, you will end up with 0.96 hours. Thanks for watching.